All right, good morning. Let everybody take a seat for a moment. All right, welcome to the Society for Industrial and Applied Mathematics Invited Talk at the Joint Math Meetings. Today, we're very happy to welcome Dr. Stephen Lee from the United States Department of Energy, Office of Science, Office of Advanced Scientific Computing Research, or ASCR. Dr. Lee is a Department of Energy Program Manager in ASCR. His main areas of expertise and responsibilities are in co-leading the Applied Mathematics Program and the Scientific Discovery through Advanced Computing SIDAC Institutes program. At the federal interagency level, he is a co-chair for the Artificial Intelligence Research and Development Working Group and a co-chair for the Digital Twins Research and Development Fast Track Action Committee for developing a national strategic plan. Many of Stephen's recent leadership activities in foundational and cross-cutting R&D stem from organizing the 2018 ASCR Basic Research Needs Workshop and the report on scientific machine learning, core technologies for AI. Before becoming a program manager in DOE, Steve was a DOE lab researcher at Oak Ridge National Laboratory and Lawrence Livermore National Laboratory. His areas of expertise include large-scale linear algebra methods, multi-scale ODE solvers, and high-performance computational science. Steve has also been a visiting assistant professor in the MIT Mathematics Department for 3 semesters. Since his graduate student days at the University of Illinois at Urbana-Champaign, Steve has been a member of SIAM and active in the applied mathematics research community. Steve's technical interests in ongoing community interactions continue to inform his thinking and program management plans for the future of advanced scientific computing research. Today, Dr. Lee will present the lecture, Scientific Machine Learning for Accelerated Discovery and Innovation, a Program Manager's Program Manager's Perspective.
Thank you for the kind introduction, Carol. Okay, this is my first joint mathematics meeting. I've been looking forward to coming to Seattle and this event since I was invited for this talk last year, so very good to be here. The JMM theme this year is a great one about the future and mathematics in the age of artificial intelligence. As a program manager in DOE, I want to talk about this notion of AI and machine learning for accelerated discovery and innovation. Okay, so DOE, most people think the E stands for everything. That is not true, but you may think that way after I get done talking about it. I see a lot of familiar faces in the audience. I'm just curious, by a show of hands, of who works at DOE, and do you know people who work for DOE? I see a few. Okay, so I'm going to go into a little depth about DOE just for context and background. So I'm in the DOE, so there's many parts to DOE. I am in the DOE Office of Science, and we are a mission agency at about $8 billion a year. And the mission is, as you see here, it's delivering scientific discoveries and major scientific tools to increase our understanding about a number of things. So DOE Science supports a wide range of researchers at different organizations. So it's over 34,000 researchers across over 300 institutions and our 17 DOE national laboratories. Of those 17, we classify 10 of those as Office of Science labs. And at those Office of Science laboratories, there are these amazing scientific user facilities that I'll say a little bit more about now. So here's a snapshot of the 17 DOE national labs and where they're located. The one closest to us here in Seattle is Pacific Northwest National Lab. And there are different types of national labs. There's Office of Science labs, National Nuclear Security Administration labs, and others. So they're scattered about the country. Some of you have been there, some of you work there. So of the Office of Science labs, the 10 that I mentioned, they have science user facilities. Now these can be experimental facilities. They include light sources and X-rays, neutron sources, accelerators, fusion facility, things like that. And these experimental facilities generate massive amounts of scientific data. So it'd be highly in our interest to take as much advantage as possible of the data that's being generated. On the other hand, we also have computational facilities. It's highlighted in the green box there, and those are owned and operated by OSCAR, the organization that I'm in. So that is where we have our high-performance computing and our extreme scale networking facilities. So taking a deeper dive on those ASCR facilities, they're a tremendous resource. So not only do we have world-class research, we have world-class facilities. We have exascale, 1 billion flops, high-performance computing at Argonne and Oak Ridge. And then at Lawrence Berkeley National Laboratory, we have Office of Science high-performance computing resources, and it's the home for our networking facility, ESNet. I will quickly note that DOE owns and operates some of the world's fastest computers. There is a top 500 list that is maintained, I think, on a semi-annual basis to keep track of who's number one. Number one is actually at Lawrence Livermore National Laboratory now, which is an NSA lab, and they've exceeded the exascale barrier as well. So that is El Capitan. So here's a portfolio of the offices in the Office of Science. So OSCAR is one of several others. So OSCAR is for the scientific computing and networking aspects of it. Then the other are for basic energy sciences, physics, fusion, and other areas. So basic energy sciences, BES, their mainstay is chemistry and material science. BER is the home of biology and climate science. We also have fusion and different types of physics. And you quickly see on the right there what their main roles are. So in terms of OSCAR itself, we have a program structure. So we have 3 divisions. I've mentioned the facilities division briefly about the high-performance computing and networking. We also have a 3rd division called Advanced Computing Technologies that looks at more of the emerging technologies in computing, such as neuromorphic computing or quantum computing. And then the division that I am in, that has a long name, but it's really the home for the basic research in computer science, applied mathematics, and working with the other offices and other areas of DOE for computational partnerships, computational science partnerships. So there's a synergy here in terms of developing the algorithms and methods and software in concert with the computer science researchers and making sure that what we develop in terms of basic research is going to be useful and needed by other computational science partnerships with the other offices. So a little more background. OSCAR, over the past 70 years since its inception, has been advancing computational science. It started with the Manhattan Project. John von Neumann advocated for the creation of a mathematics program to support continued development of digital computing. Over 40 or more years, OSCAR has a rich investment in computational science, applied mathematics, computer science, networking infrastructure. That has led to the development of the first teraflop system many years ago, and now we're at the exascale in the Office of Science user facility with Frontier at Oak Ridge. So why do we need computational science? It's the 3rd pillar of science to complement theory and experiment. So they all go together to help increase our understanding of the physical sciences and our universe. It's essential when experiments are too expensive, they're too dangerous, or too time-consuming, or impossible to do physically. So having a computational way to do some what-if scenarios or do some exploration makes a lot of sense. So it does facilitate this idea of idea to discovery and allows you to explore different areas of science. And virtually every discipline in science and engineering has benefited from DOE's sustained investment in computational science. So Office of Science and OSCAR has benefited from this Moore's law, right? This observation that the number of transistors in an integrated circuit doubles every 2 years. And transistors and circuits have continued to shrink, but that is coming to an end. So we need to find a new Moore's law. That is there some way to keep increasing our computing power and then doing it in such a way that that computing power is useful for scientific computing and computational science. Other areas that we're exploring, in addition to neuromorphic that I mentioned, is quantum computing. So there was a recent OSCAR workshop last summer on quantum computing and networking. So we've been looking at digital computing and networking for a history. We're now exploring what does it mean to do things in the quantum realm. So we had that workshop, and that report is at our OSCAR website. And I quickly took a peek, and I'm very pleased to see that there are quantum talks here at JMM. I wasn't able to go to any of the sessions, but I see that it is an area of interest in JMN, and people are already organized and having discussions about it. And then in addition to computing and exploring different forms of computing, different forms of energy efficient computing, the data question. These facilities are generating massive amounts of data. You see in the bullets there a description of what that entails, but not only do you want to generate data, but in the context of this theme this year at JMM and OSCAR looking forward, we want to make sure that we're generating data that is AI ready. It's not enough just to spit out data and not have the right metadata to understand what's there and how it's organized, that we need to rethink the way data is being generated, and if it's a way to do it so that the AI technologies that we are developing can take advantage of it. So this is just a snapshot of OSCAR, the way OSCAR as a whole is looking at emerging trends in scientific computing. There's 5 areas here. We want to continue to build on our long history of advanced modeling and simulation. So we're looking at what kind of research do we need to fund and what sort of systems will help enable advanced modeling, simulation, and visualization. We want to get a better handle on trustworthy AI and AI-ready data. What does it mean to generate that type of information and how we can use it so that the results that we get are reliable and understandable. Another area is this notion of, again, different types of computing, whether it's heterogeneous, distributed, co-designing them so that everything works together, and being energy efficient is a major area of investigation for us. With the bottom row, we have, again, developing the newer forms of the high-performance computing and networking, but making sure that extends across the edge and across our facilities and can do it at ready for exascale generation and computing. So sort of like a Internet of Scientific Things. And then the 5th area there, with these complicated systems, it's amazingly difficult to program them. So how do we look at the computer science and the programmability aspects of taking full advantage of these new systems to do the type of science that we're interested in? So again, the driver here is that the Department of Energy has a tremendous array of resources. We have computing at exascale and exploring new forms of energy efficient computing. We have data coming from our scientific user facilities, the experimental user facilities from the other offices, and we have networking capabilities to bring all that data together and combine them in new and interesting ways. And then how do we take that and enable scientific discovery and innovation? So that last year was a very exciting year for AI. If you woke up in October, you heard the news that there were 2 Nobel Prizes awarded. The one in physics, to John Hopfield and Geoffrey Hinton. The key takeaway there is that they looked at training artificial neural networks using physics. So that was a very big deal, but then it was followed up quickly by another announcement in chemistry with a Nobel Prize to the 3 people you see there regarding computational protein structure. And again, using an AI model, AlphaFold, to do this prediction of proteins and how they fold. So people were sort of expecting at least one of these Nobels at some point, but maybe that was a theme this year for the Nobel Prize Committee, that AI is the thing. So that was very good to see. So that just generates a lot of attention now in AI and using it for science and what more can be done. Digging a little deeper, I actually tuned into Dimas Hassabis's Nobel Prize lecture. It's a very good presentation if you have time to go to YouTube and check it out. But at one point in his slides, he was like, well, what is a suitable problem for AI to solve? And he listed 3 requirements. Okay, one, as you might suspect, the problem has a massive combinatorial search space. It's literally computationally intractable to do it by brute force. Okay, so you need to be smart about how you go searching that space. To help you search that space, the second requirement is that you need a clear objective function or loss function to optimize against. So you need to know what you're trying to predict and then what the ground truth is and what the difference is, and maybe that can point you in a better direction to explore. And then the third area is one or the other, but he emphasized both, either lots of data and or accurate and efficient simulators. So for me, this just pointed out that the need for efficient simulators is still going to be very important going forward, let alone how are we going to manage all the data that does come in from experiments and things like that. So this just naturally asks the questions, what other problems can be cast in this form, and what can we do about that? So I will say, AI it seems like it's been around forever now, but back in 2018, the Oscar Applied Math program started to look in this direction of AI, and we started with a workshop. How am I doing on time? 20 minutes so far? Okay. Okay, so let me speed things up again. So the theme here you see is from JMM, but I've modified it a bit. So in the age of AI for science. Okay, so looking at that, we had a workshop almost exactly 7 years ago to explore machine learning for scientific computing. Up until that point in 2018, I would often get some proposals that looked like they really helped to address Office of Science needs and challenges. And when I would read through the 15 pages, I'd go from start to finish and realize I haven't seen a single equation, or I haven't seen any math in there. And then I'd flip back to the title and realize, oh, they're doing machine learning. Okay, that they had some data, they had some machine learning tools, and they were going to apply it to some science problems. Okay, so we needed to fix that, right? We need to explore machine learning for scientific computing from an Oscar Applied Math perspective, because there's a lot of potential for high scientific impact if we look at it making advances in the underlying research foundations. Part of doing these so-called basic needs workshops are we do a pre-workshop report. So it's not like you come to a workshop and everyone just starts to meet and talk. Before the workshop starts, we send out to the invited participants a pre-workshop report that's sort of in 10 pages or so with a bunch of key references, describes where we think the state of the art is at the moment, so that we can all have a common starting point on what's been done, what might need to be done next, and things like that. So I found that as a program manager to be very helpful, to generate this sort of survey paper, have the co-chairs organize a team to put something together, so that we can all read something before we all show up. The other helpful technique that we've had is to have position papers. We cannot accommodate everybody who's interested in attending our workshops, so we typically have some sort of call for position paper that's announced in SIAM and other math societies and newsletters that we are going to have a workshop. You're invited to submit a short position paper, 2 to 3 pages, on what you see as the major challenges and what needs to be addressed. And when you send them in to Oscar, the co-chairs and the organizing committee go through and then try to find, what set of people and topics should we invite, to be part of our panels, be part of the discussion, and to help us inform writing this workshop report. So this workshop was a 3-day event, and it identified, what are the grand challenges here, and we wanted to nail down, what are the handful of priority research directions that we need to explore going forward. So there's a link there for the workshop report. Okay, so the workshop agenda very quickly. We had some plenary talks to highlight the status of machine learning, challenges, and open questions. We had panel discussions where we invited people from the Oscar facilities and the Exascale Computing Project, which at the time, in 2018, we were thinking about, how do we deliver exascale machines, and then how do we deliver the software stack for them. So we wanted to hear about where they stood and if AI and machine learning was on their radar, and other people who were relevant to our questions. We had breakout sessions, so in order to spur the conversations around applied mathematics basic research, you can see that the breakout sessions were organized around scientific computing and applied math, so numerical analysis for machine learning, multi-fidelity and reduced order models, optimization and computational complexity. So it's those sort of underlying research foundations that we wanted to hear comments and thoughts and insight from people as part of informing the development of the workshop report. So this is a very intense 3 days, high levels of in-person interactions and input. So the first day was more on brainstorming, had to refine those ideas, and third was the presentation of the priority research directions, which I will show now. We ended up with 6, and we grouped them into 2 categories. One were foundational themes. Okay, what were the basic research, the math, computational statistical foundations we needed for this so-called scientific machine learning? And then what kind of capabilities would that focus enable for and across Department of Energy? So I'll just hit the highlights that, the main foundation themes were, since we're doing this for science, we want these scientific machine learning approaches to be domain aware. So whether you're doing chemistry or whether you're doing material science or whether you're doing physics, is there some way to leverage and incorporate scientific domain knowledge into the way your scientific machine learning approach is being developed? You also want to take advantage of explainability or interpretability, making sure that the models and the way you develop things and use uncertainty quantification, that you get some, so that it's not a black box. Are there some ways you can incorporate information so that someone doesn't just get numbers back, but also has some way or some insight into how those numbers came to be and why they make sense? And then the third one is robustness. I think the new term these days is trustworthy, but you don't want flaky results. You don't want to get answers that you don't, not only do you not understand them, but you can't rely on them to give you the right answer, or you don't understand how to get the right answer. So in numerical analysis, that's just well known. You need to have stable, well-posed, and reliable formulations. You need to be able to quantify uncertainties and things like that. So those are the foundations, and today they've still held. That's the good news. And then for the capabilities, that was really a challenge because there's literally an infinite number of use cases that you could have for AI for science. Okay, and everyone has their own particular pet problems and things like that. But are there a basis of capabilities that if we could enable, everybody could benefit from them? And we broke them down into 3 categories. One is data intensive. So the scenario there is that someone that has a lot of data being generated, and they just want to be able to take that data and extract scientific insights from it. Okay, so scientific inference and data analysis, machine learning on multiple data, in situ data analysis, real time, things like that. The second one is near and dear to me because it's modeling and simulation 2.0. So you want to combine machine learning approaches with your traditional modeling and simulation approaches and get the best of both worlds. So we call that hybrid modeling and simulation. So make sure it's adaptive, make sure you can estimate uncertainties and tune the parameters and things like that. So data analysis, modeling and simulation. And then the third one is this sort of automation and decision support, that you can use AI as a wrapper around some other process, make it smarter, make it better, do smart experiments, build smart labs, and things like that. So the way the workshop came out is like, well, we'll call this the outer loop, for number 6, the inner loop for number 5, and I think we came up with no loop for number 4. Those were great ways to think about it, I think. I will quickly say it didn't catch on in Washington because when you talk about anyone here live in Washington, D.C. area? When you talk about the inner loop and outer loop, people think of 495. And talking to staffers about the inner loop and the outer loop just gets them thinking about traffic and all the wrong things. So we stuck with these, but I think informally we still think about outer loop and inner loop and things like that. So I think with a wide range of use cases, these 3 capabilities have held up very well. That when people look at their use case, they kind of identify which one or which set it corresponds to, whether they're trying to optimize something or whether they're trying to combine and embed machine learning with something else that they're doing, or just, I've got this pile of data, I need to understand what it means. So I was very proud of the committee for coming up with that. So when we finished the workshop, it took a bunch of months to finally get out the report, but we have an Oscar advisory committee that likes to check up on us and knows, what is Oscar doing? Can we give some advice? How's it going? That sort of thing. So I gave a briefing in April after the workshop, and there are basically 3 key findings here. So I was converted from a machine learning skeptic to an AI advocate. First finding was that basic research is going to be essential for developing future scientific machine learning capabilities. If that all works out with the foundations and the capabilities, the second finding was we will then enable increasingly powerful inference, prediction, and automation capabilities to deal with mission challenges. And then the third one is that, if you think about the scientific method, okay, which has been going on for 400 years now, scientific machine learning is a critical technology for transforming the way we will carry out our advanced scientific computing research. So I will give a cautionary note here. AI and machine learning is not magic, and it's not a silver bullet. It's a useful tool, and we're still exploring the best ways and the right ways to use it for the type of research that we're doing. So with that in mind, and apologies to George Box, but George Box was a British statistician. He's very well known, I think, in the verification, validation, and uncertainty quantification areas about his quote that all models are wrong, okay, but some are useful. Okay, and I think that still holds, and that's certainly appropriate in this age, for this theme of mathematics in the age of AI. So I would like to update that to 2025 to say that all models are wrong, but scientific machine learning can make them more useful. So you develop these scientific machine learning capabilities and really tighten up the underlying foundations, and your answers may still be wrong, but I think it enables a greater set of capabilities, and then people can explore, well, how do we make them more robust and reliable and trustworthy and things like that. So, okay. All right, so let me briefly go. So I know a lot of you come to these program manager talks to hear about well, what does your office fund and what have you funded and things like that. So this is a before 2018 listing. I won't go into all the details, but the great thing about having that workshop is that Oscar had laid the foundation in these research areas before we even had the workshop. We've always focused on robust and stable formulations, data analysis, multi-physics, multi-scale models, scalable solvers in linear algebra, optimization under uncertainty, and so forth. And the way we did that is by funding these, if you look at the middle column, these funding opportunities in petascale data and data at scale, multi-scale mathematics, uncertainty quantification. And on the right there you see, well, they actually fit with some of the themes that we had from the workshop, that some of the FOAs that we had, things that we funded and people had worked on and generated basic research for, would support priority number 4 on data analysis, or number 5 on multi-scale hybrid models, and number 6 on decision support and automation. So we brought a lot of those people who are funded under those programs and were familiar with them to the workshop, and they were able to help lay out, how do things look going forward with scientific machine learning. After 2018, this is a listing of the types of funding opportunities that we've had that were related to scientific machine learning. We still were funding and putting out announcements and funding things at labs in core research areas, but if you wanted to see things related to scientific machine learning in both applied math and computer science, these were the type of funding opportunities that were issued. And I just have some brief comments on the side there, but the very first one that we did in 2019 in applied math was looking at verification, validation, and uncertainty quantification. And all the way down through to 2024, we're looking at foundation models for science. So foundation models for science, if you're not familiar with those, it's like ChatGPT trained on scientific data. What sort of insights can that large language model extract from the data? Instead of training things on the internet, everything that you can find on the internet like ChatGPT does, well, if we train things on the types of data that we're generating at Office of Science and the user facilities as well. Okay, so another point is that if I had to update the 2018 in the way I was thinking about it after the workshop, here's a cartoon of what that looks like. But AI systems will assist and accelerate advances in science, engineering, and technology. Okay, so 3 ways that happens that fit the 3 capabilities is autonomous experiments. Okay, autonomous experiments at the autonomous facilities experiments are a foundation for self-driving facilities for science. Running an experiment can be very tedious and time-consuming, but if there's some way to automate that process in a well-understood way, then that could really make discoveries happen faster, maybe to look in the right directions for what the interesting results are. So that was number 6, the automation and decision support. Number 5, the hybrid modeling. Digital twins is a hot topic, that you have this sort of digital twins as an interactive, data-driven computational modeling and simulation of a real physical system. So you can think of maybe like a smart electric grid that's able to do modeling and computation to make sure it stays resilient and doesn't have cascading failures. People in smart manufacturing think of digital twins all the time. So scientific machine learning, number 5 on machine-enhanced learning, is key to that. And then the third one is the learning from massive data to extract scientific insights. So I think those are sort of like the higher level capabilities that a lot of the use cases are focusing on. And again, the scientific machine learning to support AI discovery and innovation, it's a cross-cutting capabilities for world-class research, and certainly is in line with supporting our Office of Science programs and things at the NNSA. I have that little bubble that if I have time, I will say more about it, but what does the future look like? I see 4 different areas here. One is that the future is going to be more instrumented. You're going to be attaching sensors to your infrastructure and experiments and taking measurements, and you're going to be getting a lot more data coming back from physical systems and processes that you're trying to better understand and maybe monitor and maybe optimize, but the technology is going to be there with the sensors. Interconnected, think of the smart Internet of Things. I showed a picture earlier about ESNet that we have here at Oscar and connecting all the facilities, but it's going to go more than that with wireless connections. You can think of connections to satellites and ocean buoys, and these measurements that you're taking are going to need to be able to connect with one each other and be learned from. So the world's going to be much more interconnected. What's emerging now is that the future's going to be more interactive, that you want to be able to interact with the experiments, like when you do self-driving experiments. So how do you enable those real-time capabilities? The math and computing sciences are just amazing on how you're going to enable that. And then the fourth one is a little bit out there, but I call it immersive. That as you start opening up this world to both the physical systems that you have instrumented and then their digital counterparts, being able to enter into a world where you can actually have the digital overlaid with the physical and be able to interpret information in real time as it's happening, I think is going to be a very important capability. Whether it's a MetaQuest VR headset, which mine got bricked when they did the latest update, so that's no good. Or Meta, if you went to Jan LeCun's talk yesterday, at the end he said he was wearing his Ray-Ban Meta glasses, but he just said that the digital and the physical world are going to be mediated by AI virtual assistants. That you have a physical world, you have a digital world out there, and you're going to use these headsets or sunglasses to interact with it. So these are some drivers to think about where the future is going and how we can take advantage of it for science. If you think about the immersive technology and basically strapping a computer to your face with the sensors and the computing, that is a form of energy-efficient computing. And like we did with exascale, by taking advantage of GPUs to enable the next class of exascale machines, allow this technology that Meta is investing in with the sensors and the computing and the way you're connecting people across virtual environments, that may be an area to explore in terms of efficient forms of energy-efficient computing that could be used to enable the next generation of computers. Okay. 40 minutes. Okay, so what happened, and I'm going to kind of blitz through the next set of slides. After the scientific machine learning workshop, there was some Oscar strategic planning. I mentioned that we have an Oscar advisory committee that like to know what's going on with our programs, but they also like to form committees and issue reports on what our future directions might look like. So there was a committee formed. It has a very long title, Opportunities and Challenges for AI and Machine Learning for Advancing Science. This was led by Tony Hay from UK Science and Technology Facilities in the UK. And long story short is that this Oscar committee came up with 6 recommendations. You see them listed there, but one of them was, given what we've seen coming out of scientific machine learning, we need to start thinking about the creation of a 10-year AI for Science initiative and how it would be structured, that we're going to take advantage of this Internet of Things that seems to be arising, training people who are AI literate, and making sure that it has adoption from interagency and international collaboration. So what it did also stress was the importance of long-term Oscar applied math and computer science research. I'll also note that after this report, Tony went back to UK and actually stood up a scientific machine learning group within his facility for focusing on these types of SIAM approaches for his scientific research. The labs have been very busy with having a series of workshops since 2021, 22, and then 23 on AI for science. You see there's 3 reports that you can access and download on the internet. The one from 2022 focused on, let's talk about ZOE Labs and what it means for AI and surrogate models, foundation models, capabilities for property inference and inverse design. So they did not exactly match the capabilities and foundations that we had in scientific machine learning, but you can more or less map, what they have to what we did. So I think it's still resonating with the way the labs are thinking about things. So some examples of their use cases, scientific machine learning and AI are going to enable new capabilities for predicting weather and climate. There's a bunch of critical opportunities and impacts, and still a lot of R&D that needs to be developed. So they're not just asking for more money to do work, but they're actually identifying the challenges and what needs to be addressed, and making sure it's done in partnership with industry. And there's some short-term and long-term timelines. So climate science is still important. The power grid, using AI, as I mentioned, the concept of smart grids, making sure you have a resilient smart grid. You're taking measurements, and you want to be able to make adjustments so that things stay stable and reliable power sources. Could require exascale computing to do that, but certainly a lot of basic research and applied mathematics advances. So third one is certainly relevant with what's going on in the Los Angeles County, emergency preparedness, wildfires, using measurements from drones and getting a reading on what the current state is and predicting where things are going to spread and how you can allocate resources to address those problems. That's going to be very important. Fourth area I've touched on before with advanced operation for science facilities, that we spend billions of dollars a year. Of that $8 billion budget in the Office of Science, at least I believe half of it is on scientific user facilities. So taking advantage of AI to get the most benefit out of the data and the operation of those facilities is critically important. So DOE has also sort of rolled this up into a proposed initiative. There's no money for it, but they've been sort of sketching out based on these AI for Science workshop reports and other resources. Great acronym, FAST. You can see what it spells out to be. There's a website for it. But basically new investments and new initiatives and additional investments are needed for Office of Science and NNSA and applied programs for all the reasons that you see listed here. You want to leverage our one-of-a-kind and world-class computing capabilities, expand on our foundational research in math and computer science to develop these responsibly, responsible AI techniques. You want to innovate and deliver using these cross-cutting and powerful tools. You need to stand up test beds to explore and research how these approaches perform and increase our understanding. Enable this sort of smart Internet of Things with AI embedded, and increase our capabilities for the partnerships that we have with the other offices and programs for new ways, new, better, more reliable ways to understand the science. To also support this effort that's going on within DOE, we need to think about the other federal agencies. So there's a group called NIDRD, Networking and Information Technology Research and Development, that coordinates interagency research. Okay, and they developed the first national AI R&D strategic plan in 2016. In 2019 and 2023, they made updates to it. I'm one of the co-chairs of this working group. I was part of the development of the 2019 and the 2023 strategic plan. There were 9 strategies there for how you think about advancing AI across federal agencies. You need to make long-term investments, focus on how you can come up with effective methods for human-AI collaboration, make sure it's safe and secure and things like that. So you get the idea. For the long-term research, I have highlighted there at the top with chevrons, you need to be able to foster machine learning, foster federated machine learning approaches. So when you're training machine learning on data, you don't always have all the data in one place. So there need to be federated approaches on how you can learn from the data, collectively learn from the data without moving it all to one place. So that's a priority. Research on pursuing general purpose AI systems like these foundation models. FAST is looking into that. And then developing AI systems that, for data, what about training in a virtual environment? Okay, make an accurate and efficient simulator in a virtual environment to train what happens in the real world. Things like Tesla do some of their car training in virtual reality environments, and then they still need to do a lot more testing, but also look at using it in the real world. And so, short story is DOE is certainly pursuing research in these directions. Okay, short on time. Digital twins is another area. I mentioned it before. DOE, Oscar, so I was a program manager for funding this with NSF, NIH, and Department of Defense, tasked the national academies to do a consensus study report on the foundational research gaps and future directions for digital twins. You can see a statement of task of what they investigated. There's a report available. You can either Google it or there's a QR code here. They did come up with a diagram of what an ecosystem of digital twins look out. There's basically 5 key components: the virtual representation, the physical counterpart, the interlink between the two, the bridge between the two, digital thread, physical to virtual, and the need for digital twin interactions. Underneath, you see there's a lot of mathematics that goes into building these digital twins. And there are some DOE key findings from this report. 3 more slides to go. It's more than just modeling and simulation. Think in terms, again, of interactive, data-driven computational modeling and simulation, where the interactive is between the physical and the virtual counterpart. So it's not just more of the same. We actually need new and increased research funding to take on trustworthy digital twins. Because trust, as you see there, VVUQ is going to be very important. Sustainability, it's an investment to maintain a digital twin along with its physical counterpart. So you need to make sure you're investing in things that you're going to need around for a long time and that you can benefit from the digital twin technology. And of course, collaborations are needed. So one of the recommendations were federal agencies need to come up with cross-cutting programs. And they recommend that we form an interagency working group. So short story is a fast-track action committee was formed by NIDRD in April 2024. I'm one of the co-chairs for that as well. And the idea is to develop this year, this spring, if all goes well, a national strategic plan for digital twins R&D. So we'll have one for digital twins, and we'll probably update the one for AI. If not this year, then maybe next. Okay, 2 more slides. So another big deal was this AI executive order in 2023. Directives to over 20 agencies. Oscar led the implementation in a number of different areas there. I searched through it. It was kind of hard to read because the way they number things, but there was only one focused on scientific research, and that was to have the PCAST come up with a report. And again, that's something else that you can look at, and they came up with a lot of conclusions that resonate with what we've been working on since the scientific machine learning report. So my final slide, and thank you for bearing with me, but the future of scientific machine learning for AI. So I wanted to present a program manager perspective on what that looks like, given this theme of math in the age of AI. We had this workshop in 2018. Again, we had some validation themes and capability themes, but again, no silver bullet, no magic, but all models are wrong. If you use ChatGPT and it sometimes, they call it hallucinate, okay? No one really actually understands how it all works, but even though with what they've done, it can still do some useful things. You just need to be careful about taking it at its word and investigating things and think about how you can fact check and things like that. So yeah, what can AI do in general? The future I mentioned very briefly with this going from instrumented to immersive. Those technologies and insights are guiding at least the way I'm thinking about what's the next form of energy efficient computing and how can we make things more interactive in real time, and what are the research challenges the community can help address to do that. And so this is all about preparing for the future. In the SIAM, in the brochure that we had, we did identify that for science and machine learning, human-AI collaborations will transform the way science is done. The next two bullets also agree with what was in the PCAST report, that AI systems can assist scientists in pursuing grand challenges and enable great advances, but it has its weaknesses: algorithm bias, reproducibility, and it costs a lot to train these models in their current form. And I guess the key takeaway here is that the mathematics community has a key role in realizing the full potential of AI for scientific discovery and innovation. And I just tried to share some thoughts, provide some insights on where those contributions could be directed, and that, yes, we're still exploring on what more can be done to enable this capability. So with that, I will close, and thank you for your attention.